Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss magnetic properties of coordination compounds. Last class I have discussed valence bond theory, VBT. Now I am going to discuss magnetic properties of coordination compounds. The magnetic moment of coordination compounds can be measured by the magnetic susceptibility experiments. The results can be used to obtain information about the structures adopted by metal complexes. A critical study of the magnetic data of coordination compounds of metals of the first transition series reveals some complications. For metal ions with up to 3 electrons in the d orbitals, like titanium 3+, it has d1 electronic configuration. In d it has 1 electron. V3+, it has 2 electron in d orbitals, and chromium 3+, it has d3, means 3 electrons in d orbitals. 2 vacant d orbitals are available for octahedral hybridization with 4s and 4p orbitals. Actually, if d orbital is vacant, I told you, so titanium 3+ has only 1 electron, d1. Vanadium has 2 electron in d, and chromium has 3 electron in d. Then particularly in chromium 3+, 3 electrons are there. Then 2 vacant d orbitals are available. 2 vacant d orbitals are available for octahedral hybridization with 4s and 4p. Last class I have discussed. The magnetic behavior of these free ions and their coordination entities is similar. The magnetic behavior of these free ions means titanium, vanadium, chromium, all have you can say 1 electron, 2 electron and 3 electrons in d orbitals, means all are unpaired electron, and they hybridized with 4s and 4p or 4p orbitals, 4s and 4p orbitals. The magnetic behavior of these free ions and their coordination entities are similar. Their coordination entities means magnetic behavior is similar. When more than 3d electrons are present, the required pair of 3d orbitals for octahedral hybridization is not directly available as a consequence of Hund's rule. Again you listen. When more than 3d electrons are present, like 4 and 5, then what will happen? When more than 3d electrons are present, the required pair of 3d orbitals for octahedral hybridization is not directly available. Why? As a consequence of Hund's rule. Thus, for d4, chromium 2+ and manganese 3+, they have d4 configuration, d4. chromium 2 plus and manganese 3 plus. And D5 is Mn2 plus and Fe 3 plus. And D6 is Fe2 plus cobalt 3 plus. Okay. Then in this cases, a vacant pair of d orbitals results only by pairing of 3d electrons, which leaves 2, 1 and 0 unpaired electrons respectively. Here again you listen, if D4 configuration is there, D4, in case of chromium 2 plus and magnesium 3 plus, and D5 in case of Mn2 plus Fe3 plus, and D6 Fe2 plus CO3 plus. Then in this cases what will happen? A vacant pair of d orbitals results only by pairing of 3d electrons, which leaves 2, 1 or 0 unpaired electrons. Okay. The magnetic data agree with maximum spin pairing in many cases. Maximum spin pairing in many cases. Particularly if you will study magnetic data, then you will find that maximum spin pairing in magnetic in case of magnetic properties, you will find that maximum spin pairing you will find in case of, I am talking about spin pairing, maximum spin pairing in diamagnetic cases. Okay. The magnetic data agree with maximum spin pairing in many cases, especially with coordination compounds containing D6 ions. However, with species containing D4 and D5 ions, there are complications. As for example, MnCN6 outside 3 minus has a magnetic moment of 2 unpaired electrons. In this case, MnCN6 outside 3 minus has a magnetic moment of 2 unpaired electrons, while MnC6 3 minus has a paramagnetic moment of 4 unpaired electrons. This is important thing, sir. They say in MnCl6 3 minus has a paramagnetic moment of 4 unpaired electrons. Here you will find number of unpaired electron is 4. And FnCN6 Fe I am talking about Fe ferrous FeCN6 3 minus has magnetic moment of a single unpaired electron. In this case, ferrous case, FeCN6 3 minus has a magnetic moment of a single unpaired electron. Only one electron is there. In d orbital, unpaired electron is only one. That is called single unpaired electrons. While ferrous F6 3 minus has a paramagnetic moment of 5 unpaired electrons. In this case, F6 3 minus, here 5 electrons are unpaired. Cobalt F6 3 minus is a paramagnetic with 4 unpaired electrons, while cobalt oxalate C2O4 whole 3 outside 3 minus is dimagnetic. Here remember, cobalt C2O4 whole 3, 3 minus is a dimagnetic. It has no unpaired electron. All are paired. But in all paramagnetic, I have told you, all have unpaired electrons. This apparent anomaly is explained by valence bond theory in terms of formation of inner orbital and outer orbital coordination entities. MnCN whole 6 3 minus, FeCN whole 6 3 minus, and cobalt C2O4 whole 3 minus are inner orbital complexes. This explanation of magnetic properties is given by VBT, valence bond theory. How? What is explanation? Then MnCN whole 6 3 minus, FeCN whole 6 3 minus, and cobalt C2O4 3 minus are inner orbital complexes. Inner means inner d orbitals taken part. Inner orbital complexes involving d2sp3 hybridization. Why they are showing paramagnetic? Then due to inner orbital complexes involving d2sp3 hybridization. The former two complexes are paramagnetic, means MnCN whole 6 3 minus and FeCN whole 6 3 minus are paramagnetic. Then the latter dimagnetic. In third one, cobalt is the dimagnetic, but first two are the paramagnetic. Mn and Fe, Cn whole 6, both are 3 minus, are paramagnetic. On the other hand, MnCl6 3 minus, FeF6 3 minus, and cobalt F6 3 minus are outer orbital complexes involving sp3d2 hybridization and are paramagnetic, corresponding to 4, 5 and 4 unpaired electrons. Here also, in these three cases, manganese MnCl6 3 minus, FeF6 3 minus, cobalt F6 3 minus are outer orbital complexes involving sp3d2 hybridization. Here D is from outer D. Then here again it is a sp3d2, but in the beginning, in case of this what I discussed before, that is MnCl whole 6, FeCN whole 6. In this case, coordination number was, hybridization was d2sp3. Same hybridization, but here d2sp3 inner orbital complexes was formed involving d2sp3 hybridization. But now here MnCl6 3 minus, FeF6 3 minus and cobalt F6 3 minus are outer orbital complexes involving sp3d2 hybridization and are paramagnetic, corresponding to 4, 5 and 4 unpaired electrons. Then here in every cases you have seen that for paramagnetic properties, unpaired electrons are required. In d orbitals, unpaired electrons are required for paramagnetic, and if it is fully filled, means paired, in d orbital all electrons are paired, then it will be dimagnetic. Even I have last class I have discussed, even this in d orbitals, suppose 5 electrons were there, suppose, then this out of 5, 3 are no, 5 electrons I told you. Then 5 electron means all are unpaired in d orbitals. 1 went to all orbitals. But if it is a 6, then one first orbital will be paired. If it is a 6, then 7th will be paired. Then now 2 are remaining unpaired. Then sometimes before hybridization, these two will also be paired. Means one electron will come and fill to the previous. Now out of 5, 4 are completely filled. Now out of 5, 4 are completely filled. Even it was unpaired. All were last two were having one electron. But it will be sometimes it will be paired. It will come back previous orbital and it will paired. And now one orbital will be unpaired. This empty. One orbital will remain empty. Then this empty orbital of empty d orbital will take part in hybridization. And that time it will be called D. Suppose 1D, 1S and 2P is taking part. 1D and S and 2P orbitals are suppose taking part in hybridization. Then it will called inner D, DsP2 complex it will form. Hybridization will be DsP2 hybridization, but it will be called inner. Okay. If outside D is there, but that D is not taking part, inner D is taking part, then that is called inner. It will form inner complexes involving inner d orbitals. Then in these cases, if in d orbitals unpaired electrons are there, then it will be complex will be paramagnetic, and suppose if it is all orbitals are filled, all orbitals have two electrons paired, then it will be diamagnetic. Okay. Then this I have told about the magnetic behavior of coordination compounds and explanation by VBT. Now it has some limitation, but I will come one question I will discuss, then I will come to the limitation of valence bond theory. That is one question is there, it is asked in examination. The spin only magnetic moment of MnBr4 2- is a 5.9 bm Bohr magneton. Predict the geometry of the complex ion. Okay, this question is asked in examination. Again I am reading the question. The spin only magnetic moment of MnBr4 2- is 5.9 bm, capital Bm, Bohr magneton. Predict the geometry of the complex ion. Means what will be the geometry of this ion, of this complex ion, you have to tell. Now I am giving explanation. Since the coordination number of Mn 2 plus ion in the complex ion is 4. MnBr4 means this coordination number is 4. Now one more thing to understand. 4 bromine is there, means 4 minus is there, and out of complex ion 2 charge is there. On complex ion 2 negative charge is there, and bromine has 4 negative. 4 bromine, 4 bromide means 4 negative. It means Mn is how much charge? Plus 2. Mn oxidation state is plus 2. Then plus 2 and minus 4. That is equal to minus 2. It is outside. It means Mn is oxidation state how much? Plus 2. This also you remember. Then Mn has plus 2 oxidation state, that also you are knowing. And now if we will write the electronic configuration, now it is this oxidation state 2 plus, then manganese, its oxidation state is 2 plus, then you minus it from the total. Suppose manganese is 25, then 25 minus 2, 23 electrons. Okay, if we will write the electronic configuration, it will be either tetrahedral or square planar. If you write electronic configuration, then a scope will be of only two types of scope are there: sp3 hybridization or a square planar hybridization. Okay, means here you will find D is not taking part in hybridization. D is not taking part in hybridization. Only S and P is taking part. 1S, 3P is taking part in hybridization. In one case, this is possible. Okay, and also by seeing the complex, you can tell 4 MnBr4 is there. Means oxidation number is 4. Then 4 means 2 cases are there. Simply 4 orbitals. Then sp3 or dsp2. In a simple way, you can understand like this also. sp3 or dsp2. These two are possible. But the fact that the magnetic moment of complex ion is 5.9 bm, it should be tetrahedral in shape rather than a square planar because of the presence of 5 unpaired electrons in the d orbitals. If you write the electronic configuration, then you will find that in D 5 electrons are there, 5 unpaired electrons. Means half filled, D is half filled. Then when it is half filled, then what will be happen? It should be tetrahedral. Why it will be tetrahedral and it will be not a square planar? Because of the presence of 5 unpaired electrons in the d orbitals. 5 unpaired electrons are there in d orbitals. Then it will be magnetic also. Okay. Then 5 are there. Then only S and P, 3P and 1S, they will take part in the hybridization. It will form sp3 hybridization. That is the sp3 means D is not taking part. S and P only. Then should be tetrahedral. And a square planar means if D will take part, then only it is possible of a square planar. But here 5 electrons are unpaired. Then why only one will take part? D and dsp2 not possible. Okay, because all are 5 are unpaired. 5 electron these orbitals are unpaired. And unpaired means one electron, singly paired. Hence it is only tetrahedral, sp3. Now I am going to discuss limitation of valence bond theory. Also you can tell failure of VBT, valence bond theory. Limitation, it is also called limitation. It is also called failure. Okay. Then now I am telling a limitation of valence bond theory. While the valence bond theory to a large extent explains the formation, structure and magnetic behavior of coordination compounds, it suffers from following shortcomings. Okay, these actually some limitations are there, also called shortcomings. Okay, then it suffers from, you can say, some weakness. It is also called weakness. 4 terms are there, it is used. Weakness of VBT means valence bound theory, shortcomings of valence bound theory, limitation of valence bound theory, and failure of valence bound theory. Question is asked in any form. Answer is the same. Then first weakness or limitation I am telling. It involves a number of assumptions. This theory involves a number of assumptions. Second, it does not give quantitative interpretation of magnetic data. Again I am telling you, it does not give quantitative interpretation of magnetic data. Third, it does not explain the color exhibited by coordination compounds. This is a very very weak point. It does not explain the color. Why complexes have color? This theory does not explain. It does not explain the color exhibited by coordination compounds. Fourth weakness, it does not give a quantitative interpretation of thermodynamic or kinetic stabilities of coordination compounds. Means it will not tell about the stabilities of coordination compounds. Okay, thermodynamic or kinetic stability it does not discuss. Next, fifth weakness, it does not make exact prediction regarding the tetrahedral and square planar structure of 4 coordinate complexes. That's why I have discussed this separately. I have discussed one question related to that. Okay, it does not make exact prediction regarding the tetrahedral and square planar structure of 4 coordination complexes like MnBr whole 4 outside 2 minus. And one more shortcoming is there. Sixth, that is, it does not distinguish between weak and strong ligands. Ligand is also different types. Then it does not distinguish between weak and strong ligands. Actually, ligands also has a role. When ligands we approach to the central metal ion, because they have lone pair of electrons, the negative charge will be more, and as it will reach to the central metal ion, then in d orbital also they may have some electrons, or you can tell in d orbital also that their central metal ion also may have electrons. Coordination during the formation of a complex ion, when these ligands will come, they also have electrons, and central metal ion also have electron. Then some repulsion is also possible. Then there I told you some ligands are neutral. Some have negative charge. As for example, cyanide, chloride, fluoride, iodide, they have negative charge. But H2O, NH3O, NH3, H2O, NH3, they have no charge, neutral. Then now which have charge, they may have repulsion. Then it can, if repulsion is there, then due to that there may be some, you can say, exchange in position of electrons. energy will be developed there due to repulsion. Correct? Then ligands also plays a role, whether it is a weak or a strong. Sometimes you have seen the two atoms can coordinate in one ligand. Sometimes 4, sometimes 6 ligand, hexadented, tetradented, didented. Then these ligands are very strong. Correct? Unidented are weak. Then they have not considered. VBT, valence bond theory, does not distinguish between weak and strong ligands. Then this I have discussed limitation of a valence bond theory. Now I am going to start crystal field theory. Crystal field theory. This is also very, very important theory because valence bond theory has a limitation. That's why new theory has come, crystal field theory. Already I told you ligand field theory is also there, molecular orbital theory is also there. Then new theory comes only when previous theory fails. To explain the weakness, new theory generally comes. Then now crystal field theory has come now to explain the weakness of VBT. The crystal field theory CET, also called as CFT, crystal field theory CFT, is an electrostatic model. Here you should understand this is the electrostatic model. Okay. The crystal field theory is an electrostatic model which considers the metal ligand bond to be ionic, arising purely from electrostatic interaction between the metal ion and the ligand. Here concept is entirely different. You have to consider charge. You have to consider here charge. And this theory considers the metal ligand bond to be ionic, arising purely from electrostatic interaction between the metal ion and the ligand. Ligands are treated as point charges in case of anions or dipoles in case of neutral molecules. Here this is an important point. Ligands are treated as a point charge. Okay. Point charges. Ligands are considered as a point charges and dipoles in case of neutral molecules. If ligands are neutral, in that situation it is called dipoles. Dipoles in case of neutral molecules and point charges in case of anions. The 5d orbitals in an isolated gaseous metal atom or ion have same energy. Okay, same energy. Same energy means it is called degenerate. This point is important. The 5d orbitals in an isolated gaseous metal atom or ion, gaseous metal atom or ion have same energy. That is they are degenerate, means having same energy. Meaning of degeneracy means having same energy. This degeneracy is maintained. Degeneracy is maintained if a spherically symmetrical field of negative charges surrounds the metal atom or ion. Means this degeneracy it will be maintained. It will be maintained even ligands will surround around the central metal atom or ion. Okay, This degeneracy is maintained if a spherically symmetrical field of negative charges surrounds the metal atom or ion. However, when this negative field is due to ligands, either anions or the negative ends of dipolar molecules like NH3 and H2O in a complex. In that situation, it becomes asymmetrical and the degeneracy of the d orbitals is lifted. Okay, here when will degeneracy go, will be lifted, that I am telling you now. Listen carefully. When the negative field is due to ligands, either anions or the negative ends of the dipolar molecules like NH3, H2O. Then N is electronegative, and O is again electronegative. Then here that when the negative field is due to the ligands, either anion or negative ends of the dipolar molecules like NH3 and H2O in a complex, it becomes asymmetrical and the degeneracy of the d orbital is lifted because of opposite charges. Okay. But I told in the beginning, degeneracy is maintained if spherically symmetrical. Here you have to think symmetrical, a spherically symmetrical field of negative charges surround the metal. Spherically symmetrical means one type. A spherically symmetrical field of negative charges surrounded the metal. In that situation, degeneracy is maintained. But when the negative field is due to the ligands, either anion or the negative ends of the dipole molecules like NH3 and H2O, in a complex, it becomes asymmetrical, not symmetrical. Means in case of asymmetrical, degeneracy will be lifted. Degeneracy will go. But in case of symmetrical, it will maintain. Okay. This is the important point. Then what will happen if it will be lifted? If degeneracy will be lifted, it results in a splitting of the d orbitals. When it will be asymmetric, symmetric is not there. When it is asymmetric, then in that situation, what will happen? I am telling you. It results in a splitting of the d orbitals. Means d orbital, a splitting will be there in d orbital. It will break into two. There will be two division. It will break into two parts. 5 will become 5. Now it was only 1. All were having one energy level, same energy level. But due to this asymmetric, it will be divided into 2. 2 d orbitals will come in one group, 3 will go into the other group. This happened due to the asymmetric. Ligands have negative and it is asymmetric. If ligands are negative but it is symmetric, then it will not break. Degeneracy will maintain. Means energy will be same energy, almost same. But if ligands will come with energy, negative charge, and due to that, if it is asymmetric, it is creating asymmetry, then d orbital will be divided into 2. Okay. This is the important. Means due to asymmetrical arrangement or asymmetrical results in a splitting of the d orbitals. The pattern of splitting depends upon the nature of the crystal. Nature of the crystal, because I told you that ligands will have lone pair of electron and charge also. Then repulsion will be more. Then always you can say they want less repulsion. For stability, they want less repulsion. Correct? That's why to get the less repulsion, that division will be there. It will be divided into two groups. One group will have 2 orbitals, 2d orbitals, and other will have 3d orbitals. Okay. Then now I am telling you, I am explaining you this splitting in different crystal fields. Okay, but splitting depends upon the nature of the crystal field. That's why name has been given crystal field. If you see the crystal, that time you will find ligand, central metal ion is there, ligands are there. And due to this, what type of magnetic field? Field means a magnetic field, okay, or electrical field, right? Electrostatic can say this thing model. That's why electrical field you can tell. Then here I am discussing explanation, splitting of d orbitals. Crystal field splitting in octahedral coordination entities. Okay, I will discuss in case of crystal field splitting in case of octahedral coordination entities or complex. In an octahedral coordination, entity means a complex ion, don't forget. In an octahedral complex with 6 ligands surrounding the metal atom or ion, there will be repulsion between the electrons in the metal d orbitals and the electrons or negative charges of the ligands. Already I discussed. Such a repulsion is more when the metal d orbital is directed towards the ligand. Then what will happen? Then when it is away from the ligand, obviously when this d orbitals will come in front of the ligands, then what will be? There will be repulsion, more repulsion. Front, just in opposite direction they are coming. Correct? Both are in d orbitals and ligands. Both are coming in front. That time more repulsion will be there. Hence, to diffuse this repulsion, there will be division in or splitting in d orbitals. Then in an octahedral coordination entity with 6 ligands surrounding the metal atom / ion, there will be repulsion between the electrons in metal d orbitals and the electrons of the ligands. Such a repulsion is more when the metal d orbital is directed towards the ligand than when it is away from the ligand. Thus, the dx square minus y square and dz square orbitals which point towards the axes along the direction of the ligand will experience more repulsion and will be raised in energy. And the dxy, dyz and dz orbitals, these 3 orbitals which are directed between the axes, between the axes will be lower in energy. Means first two dx square minus y square and dz square. These 2 orbitals are getting more energy, more repulsions. Okay, because they point towards the these 2 point towards the axes along the direction of the ligand. They will experience more repulsions and will be raised in energy. And the last 3 orbitals out of 5 and the dxy, dyz and dzx, dxy, dyz and dxz orbitals which are directed between the axes will be lowered in energy related to the average, related to, you are comparing with average. First two went more than average and these three went less than average. Okay, relative to average energy in the spherical crystal field. A spherical crystal field has average energy, then 2 went more than average and 3 went below the average. Thus, the degeneracy of the d orbitals has been removed due to ligand electron metal electron repulsions in the octahedral complexes. Correct? Degeneracy of the d orbitals has been removed due to ligand electron metal electron repulsions, okay, in the octahedral complex to yield 3 orbitals of lower energy, that is called T2G. These 3 are called, lower energy is called T, a small t, 2G, okay, and T2G set, it is of 3 orbitals and 2 orbitals of higher energy, that is called Iitjee set, Iitjee, okay, a small e, a small g, Iitjee set. This splitting of the degenerate levels due to the presence of ligands in a definite geometry is termed as crystal field splitting. This question is asked, what is the crystal field splitting? Then this you can say degenerate levels. This degeneracy, or you can tell a splitting of the degenerate levels due to the presence of ligands in a definite geometry is termed as crystal field splitting, and the energy separation is denoted by energy separation. What is the difference of energy? This I told you what is the crystal field splitting, and the energy separation is denoted by delta P, okay, delta O. Delta O, the subscript O is for octahedral. O means octahedral, delta O, okay, delta O, you can tell it looks like a 0, you can tell O. Then this energy separation is denoted by delta 0 or O, delta O, you can, this O is for octahedral. Thus the energy of the 2 Iitjee orbitals will increase by 3 by 5 delta O. Actually, 2 orbitals increase the energy, then it will be, what will be its value? The energy of the 2 Iitjee orbitals will increase from the average. From the average, it will increase how much? Then by 3 upon 5 delta O, 3 by 5 of delta O, and that of the 3 T2G will decrease by 2 by 5 delta O. Means whatever value was, or whatever value is for delta O, then 3 5 it will, 2 orbitals will increase by 3 by 5. 3 by 5 of delta O, 3 by 5 delta O, and that of the 3 T2G will decrease by 2 by 5 delta O. If both you will add, it will become 1. 3 by 5 plus 2 by 5, only 1. But here division is there. Then this value is asked in examination. Then in octahedral cases, it will increase by 3 by 5 of delta O, and 3 T2G will decrease by 2 by 5 delta O. The crystal field splitting delta O depends upon the field produced. Field means this electrical field. The crystal field splitting, that is a delta O, depends upon the field produced by the ligand and charges on the metal ion. Some ligands are able to produce a strong field. In which case the splitting will be large, whereas others produce weak fields and consequently results in a small splitting of d orbitals. In general, ligands can be arranged in a series in the order of increasing field strength, and this series arrangement is called a spectrochemical series. Then now I am telling you how different ligands are arranged, what according to their field strength. Okay. In general, ligands can be arranged in a series in the order of increasing field strength. Now I am telling you, iodide ion is less. It will create a less field than bromide ion. Bromide ion is less than thiocyanide, SCN 1 minus, all are 1 minus, and SCN 1 minus is less than chloride ion. Okay, iodide is less than bromide ion, bromide is less than thiocyanide, and thiocyanide is less than chloride ion, and chloride ion is less than S2 minus, and S2 is less than F minus, fluoride ion. Now again you listen, is this F minus 1 is less than OH hydroxyl ion. OH ion is can say more strength than fluoride ion. Okay, and OH ion is less than oxalate ion, C2O4 2 minus, and this oxalate is less than water, H2O, water less than H2O, and this H2O is less than NCS 1 minus, and this NCS is less than EDTA 4 minus. 4 minus is there, then you can understand only. Okay, then NCS, N means carbon, C means carbon, A sulfide, you know. NCS, actually I told you one is SCN. When it is joined with N, if metal will join with N, then it will call SCN. Okay, when it will join with S, then it will called NCS. Thiocyanate, isothiocyanide. Okay, thiocyanide and isothiocyanide. NCS is called isothiocyanide. And this isothiocyanide is less than EDTA, 4 negative. And this EDTA 4 negative is less than NH3. And this NH3 is less than ethane 1,2-diene. Ethane 1,2-diene, EN. And EN is less than CN, cyanide, CN 1 minus. And CN 1 minus is less than CO, carbonyl. Carbonyl group is highest, and iodide ion is weakest and lowest. Such a series is termed as a spectrochemical series. It is an experimentally determined series based on the absorption of light by complexes with different ligands. Okay. Now actually I will tell you about the these things, how splitting of d orbitals. Splitting of d orbitals by diagram also you can understand. I can say x-axis energy you can consider increasing energy on x-axis, and y-axis you can consider it as a splitting of d orbitals. Then here you know that orbitals will split. Then they may have, in the beginning they may have x-axis, y-axis, z-axis. No, the direction I am telling you, it after splitting it may go to the different direction after splitting. Okay, means it may go in x-axis, y-axis and z-axis. Then now suppose in the beginning 5 orbitals were there having same energy, almost same energy, correct? Degenerate or degeneracy, almost same energy, d orbitals, 5 d orbitals. Okay, and now after when ligands comes to the near the metal ion, then a splitting will be there. These five orbitals will become, or you can say will have more energy. Then these 5 which was having lower energy, now in presence of ligands, there its energy level increased. Now you can write a little up. These 5 orbitals you can write a little up. Dot you can write that. It means it has energy has increased. Okay, and after that what will happen, that when it will increase, when energy increase, then now this due to the repulsion energy increased, then now orbitals have more energy. Then now when these orbitals are coming closer, then either they will come in front, okay, just axis wise, directed towards axis, then that direction 2 orbitals will further go up from this energy level. What now this 5 orbitals we are having, after the repulsion energy level increased, then this is actually average. Now when they approaching axis wise, directing towards axis, then 2 orbitals went up by 3 by 5 of delta O, and 3 went down from the average, from this average orbital where what 5 were having before splitting, that is the average. Then 2 went up and 3 went through, came down. Then up they went by 3 by 5 more, and down 3 became less, decreased by 2 by 5. Okay, then this way they created, or it splitted, as it splitted into 2 groups. This is called a splitting of d orbitals in octahedral complexes. In the middle, before splitting, what was the energy level? That is called average energy of the d orbitals in a spherical crystal field. In diagram also you can understand that central metal will be in the middle and ligands will be surrounding. Spherically it will be surrounding. Okay, now next class I will discuss about the these things, color generation. Again it is there. Now I discussed in case of octahedral coordination entities. Now this tetrahedral also I will discuss. Okay, and now I am stopping only here because I will not continue today. It will take more time. Then in this also little more I want to discuss, that next class I will discuss. Thank you.